capital, this M is pronounced, means that mass of this beam is much smaller than mass of this concentrated mass. Then I can say, you know what, I will forget this and I will consider mostly only as a mass. Then this only is a spring. However, if this is not the case, if for example this is 1 kilogram and this is 1 kilogram, what we do is not valid. It cannot be done. That should be done differently. We will study later, how to deal with those problems. Here now we deal with simplest possible problem. Simplest possible problem is that mass is concentrate first of all, and second, this is massless beam or nearly massless beam. Okay. So for example, there is another simple example that can be done. There is such a beam, simply supported here, here and here. This equals A, this equals B. Mass is placed in somewhere here, but on distance A from the left and on distance B from the right. Okay, the formula for the so I'm applying load here. Load equals mg. So this formula is taken from strength of materials. Again, I pay attention. I can derive it naturally, but it will take about half hour. It does not make sense for us to do it. So from strength of materials book, I think that most strength of materials courses derive this formula. Most, but not all. So it equals mg divided by 3ei. Pay attention, again this 3ei comes into play. But it's not always. It is just in these two problems we have 3ei. And then in parentheses, ab divided by a plus b squared times a plus ab divided by a plus b squared times b. Okay? And this can be finally written like this, mg divided by 3i, a square, b square, a plus b. So again, this whole system then is reduced to this mass, which is on some spring. And spring characteristic will be mg divided by delta. So this mg divided by this whole expression, by this expression. Then mg will disappear, and I will get something that depends upon E, I, upon characteristic of the system. I think it's very neat because suddenly strength of materials, which is also static science, there is no vibrations there. Suddenly we can use some previous knowledge from static considerations. I think it also gives an idea that there is, first of all, the universe is knowable. We can learn something about the universe. It is not conglomeration of random facts and unconnected facts. So this is very good news for us, because otherwise we as humans would be not engaging ourselves with to try to understand the world. If it was impossible to understand it, then we would not spend our time at all. But nice thing is that we see that it is knowable. I mean, we have some parts of the knowledge that are compartmentalized, like strength of material, static. Suddenly these things are important to us, also we are not dealing with them at all. That means that it is knowable. I can study something and I say, okay, I will use it in the future. Okay? So this is like a kitchen, if you want. Imagine you are preparing various foods, but the same food can be used for preparation of various dishes. So strengths of materials or statics are some foods that can be used for preparing various dishes. So to say, now we are talking about vibration dish, if you want. Okay. What often happens in education, or including university education, is that we are bombarded with so much information every single day that we have no time to enjoy. This is like living in a garden, in a beautiful garden, but have no time to look at the roses or other flowers that are around you because you have to run somewhere, etc. So I do recommend sometimes to stand and look around and smell the roses. And this is what actually we are seeing here, is that just very simple things suddenly are of much importance. So in this particular case, K equivalent equals mg divided by delta. So this is a value of K equivalent. And once I found K equivalent, I can find also the frequency. K equivalent divided by M. So vibrations, you may say, yes, but one could say, actually there is no vibrations here then, because if I found K equivalent, I find from strengths of materials. Then the formula U static divided by G, also it's, U static is a static consideration. But then where is vibrations, as if one can ask? Okay, vibrations is here because that is, we solve differential equation for vibrations. And then we were successful to recast the result in some nice form, in some familiar form. But we went through all the steps of solving this differential equation. Okay. Then the following question arises. What happens if I have here the following thing? Two springs in series, and there is a mass. By the way, one student came to me and indeed asked me again if any book is recommended or not. So my answer was that I do not demand student to purchase the book. However, if you can go to, say, half.com or any other venue, and find a book under $2, for example, then why not to buy a couple of books, each of them $2? You will have two vibration books, or just one vibration book, and you can get any book you want. You just search. It does not have to be in a new, absolutely new condition. It can be a bit used, but not very used, not such that you have to hold every page separately, naturally. But maybe if it costs $2, $3, I recommend to spend this money. That is like one cup of coffee in Starbucks. Okay, now I'm using, so in this, the question is, in this particular case, I also would like to replace these two springs by one spring. So that is my, maybe the next topic would be equivalent, okay, springs in series. Let us write down. Okay, first of all, let us note what we did before is static representation. What we did today of natural frequencies. Then 7, or maybe I should have given these titles before. From elastic body, that is this example, to a single degree of freedom system. then 8. Now that will be springs in series. Okay. So now we deal with springs in series. So I have two springs connected in series and mass applied here. I would like to replace it by a single spring. So let me show here. I would like to replace this by the following. K equivalent. Okay? How much is K equivalent? Naturally, that this K equivalent depends upon K1 and K2. Is a function of K1 and K2. Okay, so how does it depend? Okay, the answer is given here. What is used? Static displacement. Static displacement, when I'm using this load, I can imagine that this first spring displaces, then second spring displaces. So therefore, we have total displacement equals delta 1 plus delta 2. Let us show like this. Now, how much is delta 1? Delta 1 is W, the load, divided by K1. Delta 2 is W divided by K2. Now, what is K equivalent? K equivalent is load divided by static displacement. Okay. Now, that is the static displacement. Now, so what we get here is as follows. Look, please. So these two systems should have the same static displacement. Static displacement. Okay, otherwise that will not work. So therefore I'm writing down K equivalent equals W, okay, divided by U static. So U static equals W over K1 plus W over K2. Okay? So that is it. Or we get as follows. W can be cancelled. K equivalent equals 1 over K1 plus 1 over K2. Or that can be done like this. This goes there and this comes here. 1 over K1 plus 1 over K2 equals 1 over K equivalent. Okay? So that is an expression if they are in series. If the springs are in series and their constants are K1 and K2 respectively, then K equivalent is such that 1 over K equivalent equals 1 over K1 plus 1 over K2. Now, okay, so that is what we wrote. So 1 over K equivalent equals 1 over K1 plus 1 over K2. Now 9, springs in parallel. Springs in parallel. So this is actually springs in parallel because, look please, this is a ground and that is also a ground. So they are actually connected to the ground. From that point of view, they are connected to the same mass. So they are in parallel. So U static equals, so there is a load that acts here and load that acts here. So N1 divided by K1 equals U static. And on the other hand, N2 divided by K2 equals also U static. Now, on the other hand, W equals W divided by equivalent is also U static. So I would like to ask you to prove that K equivalent equals K1 plus K2. So that is homework number 3, if you remember. Homework number 3 will be prove K equivalent equals K1 plus K2 for system in parallel, for system of parallel springs. So let us consider some examples. Do you remember we had this beam with mass here, mass at the tip. Now I have this mass which is actually connected with some spring here. So there is this beam and mass that is hanging on this spring, which constant is K. Now, this is actually springs in series, like this, because this guy is a spring. And we said that this tip is vibrating like in this direction. So therefore, this whole thing is a spring in this direction, because this point moves in this direction, in transverse direction. So therefore, this mass is able to move in vertical direction only. Like this. This beam, look please. This beam is acting like this. So therefore, this is springs in series. And the formula that we have is this. So K equivalent equals 1 over K1 plus 1 over K2, or then it equals K equivalent equals K1 K2 divided by K1 plus K2. So this beam is a spring with constant 3EI divided by L cubed. This spring has just K, nothing here. So then this is K plus 3EI over L cubed. Now second case. We have, look please, we have this is not a beam, this is, yes sir. Oh, do you want me to return the picture before? It's fine, I will do that. Oh. Okay.
Quick question.
Yes, please.
Did you reduce that system to, on the left?
I reduce this system to this one.
Okay.
Yeah, I mean not reduced, but I replaced actually. They are that is like this beam has K1 as its characteristics. This is like K2. Okay, so this is a product, not summation. That's a multiplication sign here. K1 times K2, K1 plus K2. And look, here is multiplications.
What are K1 and K2 on the right hand side? On the right hand side, K1.
Yes. Yeah. Please, a student asked me about K1 and K2 on the right hand side. Now let us consider torsional vibrations of the disk. So that is this one. So here again we are using some formula from strengths of materials without derivation, but it is derived there quite long. I mean, it takes a couple of lectures. So this is a disk, and this whole system vibrates torsionally like this. On the right hand side is L1, on the top is L1, on the bottom is L2. Now, torsional moment, this is a torsional moment, is connected with the angle of rotation. This is an angle, it's like deformation, okay? So that is a action, this is a result. Like this. Pi d in force power, this d is a diameter, okay, of then 32 L, and G is shear modulus. T is a torque. So therefore, this formula can also be represented as some spring, K sub T times theta. K sub T says torsional spring.
All the combined length?
Say it again?
Is L the combined length?
No. That forget now. I'm not relying to. I'm not talking about this system. I'm talking about just if I have torsion and if I have theta, then I would like to discuss when I have a beam of certain lengths, then how this connection, what this connection is.
Is that twist?
Yes, twisting or torsional moment, twisting angle. This is twisting angle. This is torsional moment. That is torsional spring. And now here, once I establish that this formula, this expression is kT, then I see that this disk is connected to the ground in the parallel manner. Okay, because this disk is connected to the ground on one hand, and it is on the other hand it is also connected to the ground. So what I should do is actually sum up. I should sum up the spring constants in order to find equivalent spring. Now, on the left-hand side, for this spring, there will be L sub 2. On the right-hand side, there will be L sub 1. Okay? But I have to add then this stiffness coefficient. So this is not a combined length. I'm adding actually reciprocals of proper lengths. 1 over L1 plus 1 over L2, etc. This K of the first part, K1, will be K here will be pi d in first power G32 L1. Here will be divided by L2. Then these two expressions we have to sum up. Okay. Any questions until now? Okay. Let me assign you one more homework. And let me reduce. Find the natural frequency of longitudinal vibration of the system. Bar is massless. These bars are massless. No mass. Mass is concentrated here. Now, what are these? So these are cross-sectional area is circular. So here diameter equals D1, here diameter equals D2, here diameter equals D3, length equals L3, L2, L1. I would at least give you the, because not everyone is a mechanical engineer, I will derive for you the displacement connection between load and displacement in a problem. Okay? So I will derive it to you, for you. So imagine I have this thing, and this is a bar, and I have this load P. Okay? Then we said that there is this sigma equals E times epsilon. Sigma equals P divided by A. This equals E times L final minus L original divided by L original. So then this is a elongation. This one. So then I will write down elongation, which equals delta, then equals what? Look, please. I have to multiply P times L sub 0 AE. It's a very simple formula I obtained for you in a second. So delta equals P times length AE. So naturally that we will have representation delta equals P divided by K, is it right, for this bar. This is a bar. So then this K equals AE divided by L sub 0. So that is a formula for a single element. Just a hint for your homework, naturally, is that here we have 3 springs in series. Thank you very much. Our class is over. Is it understandable? Is it difficult? Or it is easy? Or it is trivial? Or it is... do you have any comments? We need to start from you and then or we can start from there.
I just wanted to